As far as the title of this talk is concerned, there are three components in the title. Yeah. First one is microextraction. Then second one is thin layer chromatography, image analysis, and third one is analytical toxicology. And it is a combination of three different approaches to give a final, rapid, and simple analytical method. We have to understand what is analytical toxicology. So basically, analytical toxicology is a branch of analytical chemistry, and it deals with screening and confirmation, identification, and quantification of various foreign substances which are not endogenous to our human body. So these foreign substances or foreign compounds are generally known as xenobiotic compounds. So whenever I use the term xenobiotics, that means I will be using it for drugs and poisons which are not endogenous to our human body. Analytical toxicology can be further broadly divided in four disciplines. When any person consumes any xenobiotic or drug or poison, the drug and poison shows its effect on his body, and just to establish the fact that the person has been exposed to the xenobiotic, you have to analyze his biofluids like blood and urine samples in order to confirm whether the poisoning has occurred or not. So this kind of aspect is dealt in clinical toxicology. It is known as clinical toxicology. So clinical toxicology basically deals with ant-mortem samples for screening of xenobiotics to treat disease states. Now, suppose the person has succumbed to death, then this field will be known as post-mortem toxicology. The forensic medicine practitioner will do the autopsy on the dead body, and they will examine the internal vital organs of the body, and they will examine the symptoms, whether their symptoms are compatible or correlating with any drug and poison or xenobiotic. This field is known as post-mortem toxicology or hospital toxicology also. So basically it deals with the examination of vital organs after death to establish the cause of death and time since death. Now coming to the next level, that is forensic toxicology, when any legal angle is added to the investigation, when legal questions arises that what is the cause of death or whether the death is due to suicide or homicide or accidental, then the legal angle is added, and this kind of aspects are dealt in forensic toxicology. So forensic toxicology is very much closely related to clinical toxicology, but it deals with analysis of post-mortem samples for drug and poison in medical legal cases. Other one is environmental toxicology. It is somewhat different with clinical and forensic toxicology in the aspect that it deals with analysis of toxicants and pollutants in environmental samples. So these are the broad classification of analytical toxicology. Some authors also considered as drug of abuse screening in as a classification of analytical toxicology. But what I feel that in forensic toxicology, sometimes we also examine ant-mortem samples for the detection of drugs of abuse. So that's why it is not wise to keep that classification separately. So basically there are two kind of, on the basis of origin of samples, they can be divided in two categories. One is ant-mortem samples and another one is post-mortem samples. So as far as ant-mortem samples are concerned, they are dealt in clinical toxicology essentially, and post-mortem samples are dealt in the discipline forensic toxicology. What kind of samples we are dealing in analytical toxicology? I was discussing the nature of samples. So basically there are two kind of, on the basis of origin of samples, they can be divided in two categories. One is ant-mortem samples and another one is post-mortem samples. So as far as ant-mortem samples are concerned, they are dealt in clinical toxicology essentially, and post-mortem samples are dealt in the discipline forensic toxicology. So ant-mortem samples, mostly biofluids or blood or plasma, serum, urine, saliva, and gastric lavages are used to establish the exposure. You have to understand one concept of acute exposure and chronic exposure. So whenever a person consumes any xenobiotic or drug and poison in large amount in one instance, then it is known as acute exposure or acute poisoning. Or when any person consumes a drug or any poison over the period of time in very small doses, then this is known as chronic exposure. So bioanalysis of biofluids like blood, plasma, serum is very much helpful and useful to establish the acute exposure. However, in some cases when the chronic exposure happens, these samples are not sufficient or the compounds may got undetected by various instrumental techniques because the labels of the compounds are below detection labels. So that's why we use keratinous samples. These are basically hair and nail samples. So hair and nail samples are basically very much rich in keratin protein, and that keratin protein binds your xenobiotics, and over the time it get entrapped in the hair and nail. It is got somewhat of kind of preserved in the hair and nail samples. So if you want to establish any chronic poisoning, you can analyze hair and nail samples for the screening of drug of abuse, and even you can detect metal also, even after 6 months or 1 year of exposure. So these are basically known as calendar for chronic exposures. Now coming to post-mortem samples, when the person succumbed to the death, then you have to establish the cause of the death, whether the death has been happened due to acute exposure of any xenobiotics like drug and poison, for example pesticide or benzodiazepines. Then the tissue samples are collected by the medical practitioners like stomach, lung, liver, kidney, spleen and brain, and other samples also are there. And other biofluids are also collected, among which blood is the most common, which we receive in our laboratories for analysis. And urine are actually available in only in 50% cases of deaths, because during the process of death the urine voids, the bladder voids of the urine, and due to that mostly in most of the cases urine sample is not available in post-mortem examination. Some other biofluids are vitreous humor, that is the fluid of the eye, bile and cerebrospinal fluids. So all these samples, the collection of all these samples depends upon what kind of poisoning has occurred to the person, means nature of poison, or each and every poison deposits in each and every part differently. So suppose the one person has consumed pesticide through oral exposure, then the stomach samples will be best, because the compound will be deposited in stomach. Then if there are any volatile or gaseous poisons you have to detect, then lungs will be very suitable. The death has happened due to any drug overdose, then the drugs are mostly deposited and metabolized in liver samples. So that's why liver are very important in cases of drug overdose, and kidneys are very important in cases of metallic poisoning. So these are the samples which are routinely collected, but depending upon the nature of the analyte, where the analyte is getting deposited in the body, so we have to see particularly for independent samples. Vitreous humor is very special, biofluid, and which is not available in each and every post-mortem cases, but it is very important in cases where the putrefaction changes has been occurred in the dead body. And the vitreous humor is basically it is located in very isolated area of the body. It is contamination resistance, and it is very sterile medium. So the compounds like ethyl alcohol and many drugs can also be detected in the vitreous humor even after the 15 or 20 days, or very even after 1 month of the death, and when the dead body is very decomposed. So these kinds of the samples are particularly important in each and every kind of poisoning. So this is the generalized analytical workflow for any analytical toxicology laboratory, and it is divided in 4 parts. First is preliminary screening using color tests. Color tests are used to detect the presence of any class of drug or class of poison. For example, if the person had consumed large amount of paracetamol, then you can identify that paracetamol using cresol ammonia test. Cresol ammonia test gives blue color in the presence of paracetamol. For example, the person has consumed salicylates, or it is a case of salicylate poisoning, then you can use Trinder test. If it is a case of phenothiazine poisoning, then you can use FPN test. So there are so many tests are available for general screening, ruling out the presence of drug or poison. So at this point, or at this first step, if the test is positive, then we should go for further examination. If the test is negative, then it is considered as negative. Case is considered as negative. So now coming to the second is sample preparation. This is the sample preparation is basically most crucial, time consuming and error prone step in any analytical analysis. We do sample preparation because once you have identified that paracetamol is present in your sample, then you have to extract that paracetamol from the sample for further identification or further detection. Suppose paracetamol, or you can take the example of benzodiazepines. Preliminary screening test will be able to detect the class of drug. They can detect the benzodiazepines, but they cannot be able to detect what kind of benzodiazepine is present. For example, it may be nitrazepam, it may be lorazepam. So for that purpose, you have to do detection and identification by some previously established techniques, and one of which is thin layer chromatography. So thin layer chromatography cannot be directly performed, on the biological samples. So you have to extract your compound of interest from those samples, and this step is known as sample preparation. After sample preparation, you can do screening and detection and identification of those benzodiazepines, which I'm taking an example. And after detecting that, yes, the benzodiazepines like lorazepam is present in our sample, you need to quantify, or you need to measure the levels of the lorazepam which is present in your biological sample. So TLC is not a technique. This is the main drawback of the TLC. The TLC is not a technique which can, quantify the levels of the drug in biological samples. So that's why we need the further step, which is known as quantitative analysis. And this step is mostly performed by using highly sophisticated, costly analytical instruments like gas chromatography, mass spectrometry, and HPLC. We will be focusing on sample preparation technique and thin layer chromatography. So as I have discussed, that TLC is a qualitative technique only. It cannot do quantitative analysis. So practically, we are using two kinds of technique. One is spectroscopy and another one is chromatography. So the basic difference between spectroscopy and chromatography is on the basis of their application. Spectroscopy is used to detect and identify and quantify for any genovitic drug or poison, but spectroscopy is not able to separate the drugs and poisons from complex mixture. For separation, you have to go for chromatography. If you are having any extract which is containing your genobiotic along with some endogenous interferences like protein and small molecules which are coming from your sample, then spectroscopy will not be able to even detect your genobiotic or compound of interest. In that case, you have to go for chromatography. Chromatography is able to simultaneously separate and simultaneously identify and quantify your compounds. Even your extract is containing 10, 15 or more than 100 compounds along with your target analyte, then chromatography will be able to simultaneously identify and quantify your target analytes. So as we know that most of the biological samples, they are very much complex in nature, and they are containing so many endogenous compounds like protein, lipids, vitamins, hormones, and they interfere with your target analyte. Target analyte means genobiotics. So it is not possible to analyze those samples directly by any analytical instruments. So the goal of the sample preparation is basically to provide a homogeneous sample. Homogeneous samples means where your xenobiotics is distributed homogeneously throughout the samples, free from any interferences. Here interferences means the interferences which are coming from the biological samples like protein and lipids, because sample preparation makes your target analyte amenable for chromatographic or spectroscopic analysis. So for the accurate and reliable analysis also, we have to extract them from biological samples by various methods, and these methods are known as sample preparation techniques. And the most common example of sample preparation techniques is liquid extraction, which is known as LLE also. So during the sample preparation, what happens? We purify and concentrate our target analyte in a medium which is compatible with analytical instruments. So medium means we are just extracting our genobiotics in any organic solvent, for example, chloroform. So chloroform is compatible with gas chromatography, mass spectrometry. It is compatible with spectroscopy. It is compatible with other analytical instruments also. So this is the reason why we need sample preparation. Any sample preparation for any drug or any poison of any class, there are 4 steps are involved. One step is homogenization. Homogenization means your samples are, for example, your tissue samples are, semi-solid or solid in nature. So your target analyte or xenobiotics is get trapped in the proteins which is present in the sample, and as per it cannot be directly analyzed and directly extracted. So you have to homogenize your sample. You have to make the slurry, or like you have to make the sample in a paste form or slurry form, so that the distribution of the analyte throughout the samples is homogeneous. After that, we go for protein precipitation. This is the most important step, whether you are analyzing blood sample or whether you are analyzing tissue samples. This step is important because after entering the xenobiotics into the human body, it got distributed throughout the body organs, and during the distribution process, it makes bonds with the proteins available in the tissue samples. So that's why these proteins are very, large or very high molecular weight compounds. They get trap your target analyte. So you have to break that drug protein complex. That drug protein complex should be broken down, and the protein should be precipitated down at the conical flask, and your target analyte in that case will be free for extraction. Now coming for pH adjustment. This is also very crucial step. As I have told that uh, there are so many kinds of drug, and chemically they can be divided in acidic drug, basic drug, and neutral drugs. So pH adjustment is done to those drugs. Suppose if you want to analyze benzodiazepines, so benzodiazepines are kept under the category of alkaline or basic drug. So if you want to extract these benzodiazepines from your biological samples, then you have to adjust the pH of the biological samples towards the basic. And if you want to extract acidic drugs, then you have to adjust the pH of the biological samples towards acidic. So why it is done? Because we are doing extraction in any organic solvent, for example, chloroform or diethyl ether. So these organic solvents are not able to dissolve any ionic compound. They are only able to dissolve non-ionic compounds, or they are only able to dissolve the compounds which are in molecular form, in their molecular form. So that's why pH adjustment is mandatory if you are analyzing benzodiazepines and you are keeping your pH acidic, or if you are analyzing barbiturates and you are keeping your pH basic, then they cannot be extracted and your report will be negative. So that's why you have to understand the nature of the target analyte, whether it is acidic, basic, or neutral, and on the basis of that knowledge you will adjust the pH of the sample. And then comes extraction. Extraction is done by liquid extraction or solid phase extraction. Now we are coming to the drawbacks of traditional sample preparation methods. So traditionally we are using, or conventionally we are using liquid extraction and solid phase extraction. So as I have discussed some points previously also, liquid extraction or LLE consumes large volume of toxic organic solvents. Organic solvents, if we are using our chloroform or diethyl ether or any other organic solvents, they are basically chlorinated, and they are very much toxic to the human health as well as environment also. And we are consuming, at least for single extraction, for the preparation of single sample, we are consuming around 500 ml of chloroform or any organic solvents. So that's why it is expensive also. And as I told that we have to manually shake the separating funnel for 50 to 100 times. That's why it is laborious also and time consuming. Why? Because only one time extraction is not sufficient for full recovery of analyte. So that's why I just suggested that whenever you are carrying LLE, you have to do it 3 or 5 times. So in doing such a way 3 or 5 times of LLE, it is ensured that all of the 80% or 90% of the xenobiotics has been extracted in the organic solvent. So that's why it is time consuming. So practically we do it, and we have we have experienced that it is consuming 2 to 3 hours for extraction of a single sample. Then multiple extraction are required, as I've told. Then low recoveries. Recoveries means we should be able to extract at least more than 80% of the target analytes. But after doing so many multiple extractions, we are not able to recover more than 60 or 70% or 50% of the target analytes. That means, suppose if the compound already is very trace concentration or is a trace amount in biological samples, and your sample preparation technique is not offering very good extraction recoveries, then it will go undetected. That's why the recovery should be it should be more than 80 or 90%. And another factor is emulsion formation. Since we know that chloroform is an organic solvent, and when it is taken with biological samples, or the protein precipitate of the biological samples, which is in liquid form, they also contain very large amount of lipid. So chloroform is lipophilic. It dissolves those lipids into itself, and then the formation of the emulsion takes place. So we have to break that emulsion. So that is also time consuming, as well as it also consumes some reagents. And after that, you are getting, after breaking the emulsion, you are getting very clear extract of chloroform, but the amount of that chloroform is around 200, 300 or 400 ml, because you have done multiple extraction. You have to pre-concentrate, you have to evaporate that chloroform completely and then reconstitute it in 1 ml chloroform or whatever the required amount for the instrumental technique. So that's why these are the basic drawbacks of traditional sample preparation methods. However, these drawbacks has been significantly overcome by solid phase extraction. As we know that there is not a single sample for analysis, we have to analyze 6 to 7 samples in a single case. So although it is consuming significantly less amount of solvent, but still it consumes more than 50 ml of solvent. It is also a multi-step procedure, and it also requires very costly cartridges, and each and every cartridge may be used for 50 to 100 times only. So these are the basic drawbacks of LLE and SPE, which are traditional sample preparation methods.